Hello, relativity friends. What we've been doing the last couple of the videos is learning how to put latex to code right on our Desmos the screen here. So I'm in desmos.com/geometry, and and carrying on with that a notch the further, I got something kind of fun here. It's a really good way to demonstrate things in special relativity like time dilation and length contraction, but do it geometrically. So you're just not putting equations on a board for the student. They can actually see how that describing vectors in a non-moving frame compared to a inertial the frame, how it relates time dilation and length contraction. Okay, so this is called the Minkowski spacetime. So what we have here is the spatial dimension and the time dimension. So the way it's laid out is that for every 1 unit of space, you're traveling and 1 unit of time in this direction. Okay. And the rules are one of the principles of special relativity is that the speed of light, this is the speed of light, will bisect this coordinate, the system, right? And everyone, stationary or moving, have to agree that the speed of light is a constant. So that's one of the most important, the principles of special relativity. Now, in this coordinate, the system, we can define basis vectors, for example, a person at rest. So this would be their spatial basis vector, and this would be their time basis vector. So this person isn't moving. So it is a stationary observer, and they are moving through time, right? So it's called their world line is moving through time. So every one of these, as examples, 1 second, but they're not going anywhere. That's the point. Now, using the Lorentz transforms, and I won't derive these in this video because it would quadruple the length of this video, and they're all over the internet. Just look up Lorentz the transforms, and you'll find all of them that you want. So what we're going to do in this video is we're going to do the Lorentz transforms to change these basis vectors to that of a moving frame and change the components of those vectors into that of a moving frame. Okay, so the first thing we need to do is to define this thing called beta. All right, and beta is equal to the velocity that someone is traveling divided by the speed of light. And I got it set right now to 43% the speed of light. Okay. And now that we've got this thing called beta, we can define this other thing called gamma. And it is 1 divided by the square root of 1 minus beta squared. And you see this is called the gamma, the factor. And as I change the speed of light, you see that the gamma factor increases. I reduce the speed of light and it decreases. Okay. So let's set the speed of light to a nice number like 50%. Okay. Now, having this information, we can use our Lorentz, the transforms, and we can show the basis vectors in the new coordinate system. So this is the coordinate, the system of the person in motion. Okay. So that is their ET prime basis vector, and here is their EX prime basis vector. Now, remember what we said, that the person at rest and the person at motion have to agree that this is the speed of light and it's a constant. So that's why when we change the speed of light, you see that they approach the person at rest, and eventually they go to 0% speed of light. Gamma just becomes 1. So the gamma, the factor is 1. 1 times anything is anything. But as we speed up, you see how they scissor together? The reason that they scissor together, first of all, this is not Cartesian space. This is hyperbolic space. But the reason is because this has to remain a constant. So this person in motion and this person have to agree on that speed, this speed of light. All right. So now it's set to 60%. So now what we can do is say, what happens if we have an event? So this person at rest says there's an event happened right there. And we're going to call that vector that goes from the origin to here. We're going to call that S. Okay? So this vector now is S is equal to 3 time units. You see that? And 0 space units. So 3 seconds is when this person saw that event happen at 3 seconds. Now, what does this person see happen here? Well, that's where we use once again the Lorentz, the transforms, okay? And we get this. So what we did was use the Lorentz, the transforms to say, how does this vector component change because of this gamma, the factor? And how does this one change because of that gamma, the factor? And what we can see is that this will form a vector, if I can find it, there it is, that looks like that. So this says, the world line of the person in motion is 3.75 ETs. So I go up 3.75 ETs. And this is where this person observes the event. Okay. So the person at rest says it happened at 3 seconds, but the person at rest sees this person in motion's clock and says, no, it didn't happen at 3.75. Well, the person in motion has a clock. That's called their proper time. They say, no, it don't. It reads 3 seconds, but I see your clock. It reads 3.75. So they disagree on what this interval happened in by this gamma factor. Okay. So that is time dilation. And once again, to demonstrate for the student, I'm probably not explaining this very well, but I'm not a teacher, okay? As you change, you see everything that changes. This time dilation gets smaller and smaller and smaller until they finally are the same thing. And as you get faster and faster and faster, it gets larger and larger and larger. The difference becomes larger and larger, right? So that is the whole point of time dilation, looking at it geometrically. And time dilation is real. I'm sure you know this, that it is built into our GPS, the satellite, the system around the Earth. Otherwise, they wouldn't work. Okay, I thought that's fun. I'll see you later.